we saw with ripple counters a way to count up to any factor of 2 with the one problem that propagation delays can feed in. However, we can feed a single clock into a set of flip-flops and count up to an arbitrary number as long as we're willing to do a little work with ands and ors to get an arbitrary counter. So we begin by making a what's called a state diagram, which lists the states that we want to go to in order, and I'm illustrating it here by a count up to 5. So 0, 1, 2, 3, 4, and then again we repeat. So a set of 5 counters counting from 0 to 4. So for each one of these transitions, I need to calculate the excitation table. So for instance, if I'm in state 0, I want the next state to be 1. State 1 goes to state 2, state 2 goes to state 3, state 3 to state 4 to state 0. So these two sets of columns illustrate my state diagram, and then I have to fill in, if I'm imagining building this out of JK flip-flops, for each one of these bits I have to say whether it changes. So for instance, my highest order one I'm calling 2, 1, and 0. So here I have state 0. I want to go to state 0. I don't care what K is, but J is 0 because I want to stay in the same state. Same with J1 and K1, but I want to change my 0th order bit from 0 to 1, so J0 is 1 and K doesn't matter. Likewise, I go through all of the columns and fill in the excitation table for this with the various things that are necessary, and that's done here. But there are, I only have 5 states here. There are 3 other states that don't matter at all. They code for 5, 6, and 7, and so I fill in X's there because I don't care what any of those things are. So once I have that, each column here I can rewrite as a Carnot map. So for instance, J2, this whole column goes to this Carnot map, and I can, but I do have to be careful. Notice, well, it's easy. The last 4 all go on the second column, where I put Q2 on this and Q0 and 1 up here. But remember, rather than being 0, 0, 0, 1, I have to swap those two. So it's 0, 0, 1, 0, and then I look and see what kind of loop can I make. This is the biggest loop that I can make. That includes a 1 and something that doesn't matter, so it could be a 1, and that's going to be B and C, which is the same as saying in my diagram Q 0 and 1. Do the same thing for J1. I get C, J0. I get A bar, the primes here, bar. For K2, notice it can always be on because I can circle everything in that line and get either ones or nothing, things that don't matter. K1 turns out to be C. K0 also, I can circle everything. So now one just has to implement these things as an actual, and that's shown here. So here are my 3 flip-flops. I use JK in this case because I need the full generality of it. This is the lowest order bit corresponding to these 2. This is the middle one. This is the highest one. And so, again, for instance, K2 and K0 are both 1s. So you see that here's K0, I have a 1 there. Here's K2, a 1 there. Likewise, J2, that's here, I want to be the AND of the previous 2. So Q1 comes there, Q0 comes there, and it turns on this when Q2 is 0 and both Q0 and Q1 are on. That will turn on the next one. And when we do that, then we just follow through and we see what happens. So here's the clock coming in. So here, clock comes in. It's in a state 0. What's the feedback to that Q bar of 2? But I started with that equals 0. So that comes in. I see that's on. Q2 is 0, so Q bar 2 is on. I turn on J. Since Q0 was 0, nothing happens there. And since both of these aren't on, nothing happens here. So that's my first transition. The next time I come through and I have K equals 1 always for here, so I turn off immediately. Whenever I turn on, I'm going to turn off the next. That's definitely true of B0 and Q0 and Q2. But what happens for Q1 is that whenever B1 is on, the next time Q2 will turn on. So we see it happen here, we see it happen there. So I go 1, well, I started with 0, I go 1, 2, and then since Q2 is still off, that feeds the 1 of the Q bar feeds back and I turn on. So 1, 2, 3. Now finally, both of these are on at the same time, and that feeds in to turn on Q2, but it immediately turns off. These other two have turned off, and I've gone 0, 1, 2, 3, 4, 0 again. So that's how I design my Mod 5 counter. As a final example, here is a Mod 8 counter. It's nearly the same as the Mod 5 counter, except that I leave on B2 for as long as it needs to go. Basically what I had before for Q0 and Q1 will count up to 4 over and over again. That's easy. And before I had turned off Q2 as soon as it was turned on, but here I leave it on for a little longer, and I realized that I forgot a line. Both K2 and J2 are the same here, so I forgot to draw that line on. So it's on until what that last bit does, Q2 stays on, B2 stays on until both B0 and B1 are on again, and that's when it gets the signal to turn off.